Hi, everybody. Today we're going to talk about the importance of measuring dew point. Welcome to this webinar. My name is Pascal van Putten. I have the honor to have Frank Moskovich today with us, who is associated to Draw Professional Services. He has over 40 years of experience in plant engineering. He's focusing on auditing, consulting, training, and system design fields. And he is a compressed air challenge instructor, air master, and KGI expert, and many more. And I said, my name is Pascal van Putten. I'm CEO of VP Instruments, and my company offers industrial clients energy management solutions for compressed air, technical gases, and other utilities. This webinar is in two parts. The first part will be done by Frank, and I will take care of the second part. So let's get started. Frank, take it away, please.
Okay, thank you, Pascal. Good afternoon, good morning, good evening. I know you folks are all over the world. Let's move through these slides, and they're not very technical. It's more point. How do you get that moisture measured? How do you understand what's going on in your system? So this slide really shows all the contaminants potentially that can go into your compressed air system. You know, there's just a lot of bad things that you can be pulling into your compressed air system. Today we're concentrating on the moisture, that blue moisture. So the next slide, we actually can see, make sure I have everything here too, that the obvious, compressed air must be dried. And back in the day, no one really cared about drying the air. I mean, I was doing this now 40 years, almost 45 years. Very few customers had dryers, believe it or not. They just dumped that stuff right into their system. Today, different industry, different world. We have water that goes in. We have rust, blockages. Cold weather has freeze-ups. It causes downtime. It causes scrap. And everyone on this call that's involved in a factory environment knows exactly what I'm talking about. The only thing that you could do, and that last bullet point talks about this, is to measure your dew point. And I do a lot of studies. I do baselining, pressure, flow, power. Very few people add that fourth component of the dew point, the moisture content. And that's what we'll be discussing today, this first portion anyway. So here's a couple of pictures. And you can see there's a little pipe there with rust on it. The moisture washes away the lubricants. It causes rust. It causes scale. The wear on tools, I've got customers giving me literally $5,000 to $10,000 bills every month, not giving it to me, but showing me of their tools that have failed from water. $5,000 to $10,000 a month, and they just continue with it because it's a different budget. Sluggish operation of air valves and cylinders, malfunction, and the last bullet point, the worst, is you're losing product. You're not making money. Your product is ruined. And if you're a painter, you can have, spots or just all kinds of just little nothing that works right with water in the system. So we'll move on and we'll see what else we have. We have real, I would say these are real pictures because I know the guy that took them. And this is what happens in a pipeline with water contamination over a period of years. So this is not very pretty, is it? These are actual pictures of a customer's complaint. Was not so much the water. The complaint was pressure drop. And in lieu of the pressure drop, of course, we pulled it and we looked inside. So not only the pressure drop, but could you imagine that stuff moving down your pipeline? And that's exactly what happens. Exactly what happens. So let's talk about wet compressed air. We know that water is present in the air. This slide kind of talks about, we got nitrogen, oxygen, carbon monoxide, whatever other gases are involved that you're pulling in. But water in a vapor form is also a contaminant, and you're pulling it in. And water is gaseous, and it stays gaseous as it moves through your compressor until it comes out of the aftercooler as liquid. And we'll talk about the last bullet point, which is the humidity of the air. That's the amount of moisture in there. So the next slide actually shows a typical 25 horsepower compressor, right? Think about it, 100 CFM. And it pulls in 7.8 cubic foot of air, and where that came from, that's compression ratio. So 100 pounds out, 0 in, or 14.7 psia in, or 114.7 psia out, divide it, and you get about almost 8-to-1 ratio of compression. So we take cubic foot of air, we squash it 8 times. And if it came in 30, 40, 50% relative humidity, it's 100% saturated. And what's important about this slide is the last bullet point. Air is 100% saturated leaving your air compressor. And when it's 100% saturated, any further cooling, moisture will condense. Therefore, its temperature is its dew point. So the next slide we look at, we can have definitions of humidity, and you can get as technical as you want, but basically it's the amount of moisture in that cubic foot of air at that temperature as a ratio of what it could hold at that temperature. So obviously 100% relative humidity, it's holding everything it can at that temperature. And the dew point, simply by definition, when air is 100% saturated, the dew point is that temperature at which moisture will condense. So any further cooling and the relative humidity and the dew point match each other when we have 100% saturated air. Now we continue on with the next one, and we can see that this definition of PDP, which is, sometimes people ask me, hey Frank, I see this PDP, what is that all about? And I go, that's pressure dew point. You know, everyone talks about dew point of 35 degrees, 40 degrees Fahrenheit, or Celsius, whichever you use, but pressure dew point is what we use in the compressed air world. And that refers to the gas, or the compressed air in this case, above normal atmospheric pressure, well, obviously in a compressed air system. So that's what we're concerned with, is the pressure dew point, as compared to the atmospheric dew point on the bottom of the slide, where that's actually the temperature without any influence of external pressure. That's when the weather guy on the news gives you the dew point, that's the temperature there. Anything below that dew point, moisture will condense out. Moisture will condense out. So let's continue on and see what other definitions we might have. Ready for that next slide, Pascal? There, this is a great slide. This graphic, and if you look at the bottom on the x-axis, you'll see pressure at dew point. If you look at the y1 axis on the left, you'll see the atmospheric dew point. So the green line is a refrigerated dryer. So you go up from the bottom, which is a positive 40-degree pressure dew point. Hit that red line, which is the 100 psi mark, swing to the left, and you can see if I expanded the air to atmosphere, or atmospheric dew point, equivalent to minus 10. Now the blue line, minus 40. That's a desiccant dryer, typical, right? Maybe a heatless. You hit up to that red line, swing over to the left, and that's minus 40 is minus 70 expanded. So there is quite a difference whether you're measuring pressure dew point or regular atmospheric dew point. And you can't make a mistake between the two because you'll be in a lot of trouble. So the next slide talks about vapor pressure. And vapor pressure is how we take our measurements. So we need to know, if we're going to measure, why are we getting all this water in our piping system? Where's it coming from? Well, air has the moisture in it, and we use, in the second bullet point, it says grains of moisture per cubic foot. So each cubic foot of air saturated at a given temperature can hold X amount of grains. So let's take a look at the next slide. You'll see that 7,000 grains is equal to 1 pound or 1 pint of water. 1 pound or 1 pint. Let's take a look, and the next slide show a classic 25 horsepower compressor, again, about 100 CFM, and we're looking at 40 hours. So I bring in 100 CFM, and over a 40-hour period, that's 240,000 standard cubic feet, right? Think about that. That's 40 hours. Now, I don't have a dryer in this system, so what's going to happen? The air coming out of my compressor is about 80 degrees. It's 100% saturated, therefore the temperature of the air is its dew point. Any further cooling, moisture will condense. The piping is 70 degrees. So you can see a couple of bullet points down. Is that 10-degree reduction a big deal? Well, let's see. We'll move on and we'll see what's happening here. So 80 degrees, the first bullet point, if I had a grains of moisture chart, and you'll have to take my word on this one. We don't have the time during this webinar to pull it up, but 1.42 grains for every standard cubic foot at 80 degrees. And at 70 degrees, it's 1.03 grains. So I got to dump out 0.39 grains per cubic foot over that 240,000 standard cubic foot that passed through the pipe in that 40-hour component time. And if you look at the next slide, you'll see that if you multiply it, it's 7,000 grains is 1 pound or 1 pint. I divide it, so just a 10-degree drop without the dryer, 13 pints or almost 1 3/4 gallons condensed out. Now, if you're running 24/7, you could hit 40 hours, right? Two 24-hour days is 48 hours. So less than 2 days, you've already got almost 2 gallons of water if you don't have a dryer. All right? Let's take a look at it. Let's continue. Let's go on some more. Now, this is just the dryer issues, but I want to talk about this slide because customers that I visit that have water problems downstream, again, you got to remember, no one's measuring this. They have dew point monitors maybe in their dryers, maybe, if they're lucky, especially with refrigerated dryers, it's very rare to find that. And they complain of water downstream. What are they complaining about? Well, is it a dew point issue? Is it the ambient conditions? Or is it mechanical? Now, this is a water separator and trap that's the immediate outlet of an aftercooler of most air compressors. In the bottom of that separator and trap, there's a little ball float. This is a certain design that uses this. And if a customer hard pipes that to a drain and never sees any condensate, they'll never know whether that drain is clogged. Therefore, that 75% of the water that aftercooler should have taken out as bulk liquid continues on its merry way down into your piping system. You might have a wet tank. You might be lucky. Who knows? You might not have a wet tank, but it goes downstream. So that's the problem. We have to fix it. Mechanical issues cause moisture problems downstream. Here's an updraft aftercooler, obviously not maintained. On the left side, right, so you have an oil cooler and aftercooler. The aftercooler is going to send very hot air, if it's not cooling, to the dryer, which is going to create a problem, send moisture downstream. If you're not measuring your dew point, you will never know these things are occurring. These things occur all the time. I can probably add up 1,000 companies that I visited that have water in the lines, all due to mechanical problems, not ambient. So now let's take a look at a system with a dryer. We're going to put a dryer in there. All right, so here's a classic compressor, wet tank, almost a best practice. If this was a best practice, it would have a dry tank too. But let's just look at this. So the dryer is doing its job. You think it's a 50-degree pressure dew point. Most people think their dryer should be 35-degree dew point. This is Fahrenheit now, 39-degree dew point, right? But if you're not measuring, you don't know. And dryer heat exchangers, they can foul up. They can have a problem. There could be hot environments. So let's just say it was a 50-degree pressure dew point. And downstream, the piping, somehow, it was a cooler evening, 40-degree ambient temperature Fahrenheit. What about that 10-degree reduction? Well, let's go to the next slide and let's look at the grains. So we know that this 523 point, again, with the chart, I don't have it in front of you, but just take my word. At 50 degrees, there's 0.523 grains of moisture per standard foot, right? At 40, the air can only hold 0.3654 grains. And that is 100% saturated. So I got to drop out over that 40-hour period. I have to drop out into liquid 0.1576. Well, multiply that by the 240,000 cubic foot of air that went by in that 40 hours, and the next slide shows you that we have this issue. We have 7,000 grains is 1 pound divided into that 37,824, and just that 10-degree reduction after the refrigerated dryer, 5.4 pounds or about 5.4 pints. I guess you beer drinkers would know what that feels like, what that is. 5.4 pints of water. Right? That's almost 3/4 of a gallon. And why did it happen? No one knows except the fact that I dropped the temperature below the dew point by 10 degrees. Simple. It happens all the time. This was a dry tank, obviously not working very well, and they don't even have an automatic drain on the bottom. You do not want this to happen in your system. Definitely do not want it to happen in your system. So let's take a look at what else could happen. Let's talk about wet compressed air. You have to know what dryer to buy. Now, I've been in this business a very long time, and I'm in Phoenix, Arizona. And my customers here, the ambient conditions do not dictate a desiccant dryer is required. Our temperatures here are usually in the hundreds, obviously. So refrigerated dryer is quite fine. Yet I have customers that have desiccant dryers, heatless desiccant dryers. I go, now why did you do that? Why did you buy that? And they go, well, we had moisture in the lines, and the vendor came in and said, let's just put you with a desiccant dryer. We'll really fix the problem. And guess what? They still have water problems. Reason? It was mechanical issues, nothing to do with the ambient conditions. Now, water. This is basic stuff here. Water vapor will always move from an area of high relative humidity to an area of low relative humidity. So basically, in your pipeline, depending on what dew point you have created, you've created this imbalance. It's just, it just doesn't want to be there, and the outside air, ambient conditions, they want in. So an air leak can allow water vapor into your piping, which we'll take a look at in another slide or so, but liquid water will always form. And if you do form it, it's going to go by gravity to wherever the low-lying area is, right? The bottom bullet point. Liquid water left to stand in receivers, filter housings, evaporate. Customers have a problem with their dryer. A bunch of liquid went through, and it sits in this low-lying pipe area, and everyone's happy. And 2 weeks later, a guy is blowing down his machine, creates a high velocity in the pipe, and wham, all that liquid comes out. Nothing to do with the dryer failing. It happened weeks ago. So let's take a look at what happens after this. We have water in the pipe. We want to get it out. And those of you that have problems with pressure drop, maybe your pipes are undersized, especially in the compressor room, your velocity of air is probably fast enough to actually whip the condensate past the traps into your system. So if you are going to do that, be aware of that the velocity of air is a factor, right? And the last bullet point, those of you that have removable condensate by any method, even if it's a ball valve, just think about zero air loss drains. And that's what you want to do, zero air loss drains. So we're coming to the end here, and I want to bring back the fact that an air leak can cause deterioration. Now again, the overlying premise here is this is happening to everybody. Regardless of how great you think your system is, this is happening. There's a combination of Fick's law, F-I-C-K-S, also the Joule-Thomson effect. The Joule-Thomson effect is as air expands, it cools. A gas expands, it cools. So basically, you got this pinhole here, right, coming out, and a small pinhole, that air, you just let the air out of a car or a bicycle tire, you can feel it on your thumb or your finger how cold it gets, right? So the water condenses because the humidity on the outside is not that great. So water droplets will condense, and it will literally migrate into the pipeline, and it'll diffuse right through that, even as small as a hole, and now you've just upset your dew point. When I do measurements, I'll measure the dew point in the compressor room, and I'll do multiple measurements out in the demand. There is 95% of the time always a difference. Now the next slide is more about Fick's law. Fick's law. That's molecular diffusion. I know this sounds very weird, but there's a cross-section of a pipe. In that pipe, the pressure dew point is minus 40 degrees Fahrenheit or Celsius in this case. The vapor pressure, 0.001861 psig. Outside, the air is 60 degrees Fahrenheit, where the vapor pressure is 0.2563. What a ratio that is of difference. Don't you think that wants to come in? So on the right-hand side, let's take a look at some of these bullets. Water and air will always seek to reach equilibrium. So remember, you've created this terrible scenario in your pipeline, and it wants to balance out. It's not terrible. You need the dry air, but you've created this imbalance. So any dryer will create unstable gas, and it wants the water vapor back in. It will get in any way it can. Third bullet point, if entire compressed air supplied to minus 20, the piping must be completely free of leaks or the dew point will degrade. I have hundreds and hundreds of data collections showing just this effect. And I have customers that want to go down to minus 80, minus 100. And before we go to the bottom bullet point, take a look at the bottom left of the screen. If I go to minus 100 degrees dew point, it would be 11,192 times a difference of vapor pressure, so that's why it degrades. The bottom right bullet point, maintaining such a dry condition would involve welding every connection throughout the entire pipeline. So before I turn it back over to Pascal, I want to just let you guys realize one thing. You do need your dry air, absolutely. Just don't let it be determined by a mechanical problem. Always identify that first. If ambient conditions dictate you need a desiccant dryer, make sure you have monitoring. And Pascal's going to talk about what we do to monitor. Without monitoring, you look at your desiccant dryer, you go, hey, it's minus 40 degrees, it's doing great, yeah, everything's fine. Measure out there in the demand, get some sensors. And that's my part of it. I'm going to turn it over to Pascal, who's going to talk to you about how to do that.
Thank you, Frank, for this first part. And yeah, let's talk about how to measure and monitor dew point and why you should do this. Yeah, Frank told already a lot about that, why you should do it. It will prolong the lifetime of your equipment. It will help you to reduce maintenance costs. And in critical production processes, it will help you to guard end product quality, and as the painting example, but also prevent costly production losses. I had an example of a food manufacturer for animal food where the food was dried, but the powdery food was transported with compressed air. And in that case, you really need dry air, because otherwise you get, in the end, all kind of fungi in your warehouse, in the stored product, in the stored end product, which you don't want, of course. Well, there are also some cases where even a dew point sensor would not really be of much help. We sometimes run in these cases where sensor is between brackets malfunctioning, but actually this is often caused by a mechanical issue, like a failing drain or something else broken, like for example, a water separator that's not working properly. So in that case, you might just want to open first some of the equipments to look inside, or to look under equipment if you see water on the floor. Now, where to put a dew point sensor? Typically, you place it close to the dryer, in the outlet of the dryer. That will give you the quickest response time when dew point is changing. But you could also place a sensor downstream of the dry receiver tank. But remember, in that case, the air in the receiver tank, it takes, of course, time to replenish that air. So your response time of the dew point sensor will be a little bit slower. If you look at desiccant dryers, it's basically similar to the refrigerant dryers. You place the sensor downstream. Although if you have a heat regenerated dryer and there is some problem with the heat regeneration, you sometimes get this very hot air getting out of the dryer into your pipe, and that basically that sweep of temperature could affect the reading of your sensor temporarily. In systems where you have parallel drying, we advise to put sensors on each dryer. That will help you to see which dryer is doing what, and if there is a malfunctioning of one of the dryers, you can have an immediate signal. If you want to save money out, then you would place it in the collected in the line where the two dryers are feeding in. You could do that, of course, but in that case you will get a mixture of the two dew points, and you still need to figure out which dryer is causing the problem. When you install a dew point sensor, it's advised to use a sample block, and this is basically because you want to have continuous flow over the dew point sensor. You can also do that by mounting the sensor directly into the pipe, but be aware that the sensor could be impacted by particles or oil. So then there's always a protective cap around the sensor, but it could get fouled. And also the signal will be slightly dependent on the demand. So the higher demand, you get quicker refreshing of that air, so you get a different response time. If you use a sample block, then you have always an identical continuous flow over the sensor. And because the sensor is not straight into the flow, it has also the benefit that it prevents the sensor from fouling and direct impact. But remember, these sample blocks, they have a small valve, and it's best to use them with a small needle valve and not using a big ball valve, because you want to limit the energy loss by not opening that valve too much. You also want to limit the temperature effect on the sensor, because if you have too much flow, the air cools down a little bit and you can get a lower temperature. And of course, you're affecting the pressure dew point reading. So if you lower the pressure too much in the cell, you're actually measuring something in between the pressure dew point and the atmospheric dew point. And you have seen the graph in the slides of Frank that can make a huge difference. Now, a more advanced way to monitor dew point is to combine a few things. You could install a flow meter upstream of the dryer, and then a flow meter that's designed to measure wet air. And you have also 3-in-1 flow meters, so they measure flow, pressure, and temperature at the same time. And if you combine it with dew point and even with a power meter, then you can see a lot more. You can see, for example, inlet temperature problems. If the inlet temperature of a refrigerant dryer is getting too high, the dryer will it will be hard for the dryer to cool the air down, so it will have an effect on the dew point. You can also see if the dryer is maybe undersized because the flow is too high. Now, if you would add another pressure sensor downstream, then you can see pressure loss over your dryer or the entire air treatment, which can mean that you need to replace filters, but it could also mean that the dryer is internally fouled by something. And if you have the power, then you can also basically see the efficiency of your dryer and compare it to other dryers and use that to optimize maintenance, for example. Or when you're selecting a new dryer, you could use this data basically to select the right new technology for your plant. And when it comes down to drying, it's always a trade-off between how dry do you need to be and how much energy you want to use, because drying air is not for free. So it's important to realize this when specifying how dry the air should be in your plant. And in the next few slides, I will tell you more about that. So how to take the right dryer for the right application? Well, in that case, you should consider, do you really need dry air in the entire system, or can you basically dry air only for specific areas in your plant? Another thing to consider is, do you need a low dew point all year round, or is there a seasonal influence? And in some cases, can you prevent those temperature drops that Frank showed in his slides? Basically, if you can isolate the pipe, then you could prevent condensation happening. And a good example of that is if you have multiple buildings and the piping is outside. During wintertime, of course, you get condensation problems in those pipes, but why not isolate them or even run them close to steam lines so they keep warm, and then you will have less problems with condensation. Typically, if you look at the different dryers, you see in this table also what it takes, to run them. If you take a refrigeration-based dryer, it's about 0.8 kilowatt per 100 CFM. A desiccant is 3 to 4 kilowatts per 100 CFM. So it's a big difference in energy costs. A dry receiver tank can also be very helpful because it basically protects the dryer from overflow when there is a peak demand. It also will help you to size basically the dryer based on average flow rather than that peak demand. So it has a double function, and of course it helps you also to get a more stable pressure, and it helps you with sizing the right compressors. But that's another story. What's also very important if you have desiccant dryers in your plant, especially heatless dryers, to look at the purge flow. Typically, purge flow is specified 18 to 20% of the nominal flow. However, what's on the nameplate is not always what's really happening with these dryers. In some cases, purge flow was set too high. It could be due to a maintenance job that was not done properly or during commissioning. So it's good to check if the purge flow is at the most optimum level. And one way to do it, we did it in a project a couple of years ago, is to guard the input flow with a wet air flow meter and guard the outlet flow of these dryers. And in that way, we were able to see basically what came out of the dryer in terms of purge flow. If you nowadays buy a desiccant dryer, they can be offered also with dew point control, which is a very good choice because then the cycling of the columns is basically timed based on actual dew point instead of based on just time. And another trend in the drying world now is hybrid drying, where you would combine a refrigerated dryer with a heated desiccant dryer. And this then in a tandem configuration. And this way, the control system that controls those dryers can make the right decision on when to use only the refrigerant dryer and when to use also the desiccant dryer. And that another advantage is, of course, that the air is pre-dried, so the desiccant dryer has an easier job to take out the remaining water. When you specify for a new plant or when after an audit for an existing plant, you can use the ISO 8573-1 directive to specify basically what type of dew point class you need for specific areas. So this is a good starting point and a good guideline for that. So for instance, you could say, well, for the entire plant, we want to have at least class 5, but for specific areas, we want to have class 3 or class 1 or whatever you need. And that way you can make sure that the vendors that will eventually advise you which type you need, they can make the right choices based on your requirements. And this can save you a lot of energy costs, of course, down the road. Eventually, permanent monitoring is really the key to keep everything running at the optimum level. If you combine dew point with flow measurement, with power measurement, and basically monitor the entire system, then you can collect data on the system behavior the whole year round, 24/7, 365 days a year. And when there is an event, maybe caused by too much demand downstream, or maybe because of the compressor running at a too high temperature, you can basically really trace down the root cause of that event. And it might be not always the dryer that causes the problem. So permanent monitoring in the end will help you to make the right decisions for maintenance, but also make the right investment decisions for future expansion or optimization of your compressed air system. So to summarize, maintaining your dew point is very important to prolong the lifetime of your equipment, to reduce maintenance costs and prevent production losses. But be aware that you dry only where necessary and only to the pressure dew point that's really required. Don't overdo it, because that will be a waste of energy and a waste of money. And permanent dew point monitoring is in the end the key to prevent damage to equipment and products and to make the right decisions on time. And what's of course very important is that you should address decaying dew point issues before they will cause serious issues and costly production losses. So all right, so I guess this is the end of the webinar for today. Thank you all for watching, and Frank, many thanks for your contribution. It was very good. I learned also a lot of new things on dew point.